In this video, we will solve basic logarithmic equations. We will use the facts that logarithmic and exponential functions are one-to-one and inverses of each other to solve equations. In particular, we will use the fact that if x equals y, then a to the x equals a to the y. This says essentially that we can apply any exponential function to both sides of a given equation. Also, we will have the converse statement that given equal exponential expressions with the same base, the exponents must also be equal. We can also apply any logarithmic functions to both sides of a given equation. Thus, if x equals y, then log base a of x equals log base a of y. Of course, we have the caveat that x and y must actually be in the domain of the given logarithmic function. Hence, x and y must both be positive. Since logarithmic functions are one-to-one, we also have the converse statement. If log base a of x equals log base a of y, then x and y have to be equal. Finally, we will frequently utilize the inverse relationship between the exponential and the logarithmic functions, that y equals log base a of x if and only if x equals a to the y. Let's illustrate the application of these problems to solving equations. We consider 6 specific examples. Let's first solve the equation 3 to the power x minus 5 equal 81. We start with the given equation and note that we have an exponential expression on one side. Rewriting 81 as 3 to the 4th produces equal exponential expressions with equal bases. Therefore, the exponents must be equal. We can solve the resulting linear equation for x by adding 5 to both sides. We get that x equal 9 is the solution to our equation. Plugging x equal 9 into our original equation, we get that 3 to the 9 minus 5 equals 3 to the 4, which is 81, so our solution checks. For our second example, let's solve the logarithmic equation log base 2 of 32 equals 3x plus 1. We start with the given logarithmic equation and notice there are multiple ways to proceed. One way is to evaluate log base 2 of 32. Recall that log base 2 of 32 is the exponent to which we raise 2 in order to obtain 32. Since 2 to the 5th is 32, log base 2 of 32 is 5. Now we have a linear equation to solve. This time we can subtract 1 from both sides and then divide by 3 to get that x equals 4/3. Again, we can check into our original equation that 3 times 4/3 plus 1 equals 4 plus 1, or 5, which is indeed log base 2 of 32. Now let's solve the equation log base 4 of 3x plus 7 equal 3. We start with the given equation, but notice this time the logarithmic expression is not easily evaluated. In fact, there are restrictions on the domain in this problem. We need 3x plus 7 to be positive in order for the logarithmic expression to be defined. Thus, we will have to check our eventual answer for extraneous solutions. This time, we can convert our given logarithmic equation to the equivalent exponential form. To get 3x plus 7, we must raise the base 4 to the power of 3. Replacing 4 to the power of 3 with 64, we get another linear equation to solve. We could subtract 7 from both sides and divide by 3 to see that x equals 19. Plugging x equals 19 into log base 4 of 3x plus 7 gives us log base 4 of 57 plus 7, or log base 4 of 64, which does indeed equal 3. Let's consider a similar problem and solve log base 2 of 7 minus 3x equal 4. Again, we start with the original equation and notice that we will have to check our final solution for possible domain problems. We convert the equation to exponential form, then evaluate 2 to the 4th as 16, and we have another linear equation to solve. Subtract 7 from both sides and divide by -3 to produce that x equals -3. A negative solution isn't automatically extraneous, but we do need to check this solution. If we plug -3 into our original equation, we get log base 2 of 7 plus 9 is log base 2 of 16, and that is indeed 4. So the x equal -3 is a solution to our equation. Ramping it up a notch, let's solve the equation log base 2 of x squared plus 7x equals 3. This equation is similar to the previous two, so we might try the same technique. That is, convert to the equivalent exponential equation, replace 2 cubed by 8, and now we have a quadratic equation to solve. We could subtract 8 from both sides to put our quadratic equation in standard form. Fortunately, the quadratic x squared plus 7x minus 8 factors, so we have a product equaling 0. We set each of the factors equal to 0 and solve for the variable. We get that x equals -8 or x equals 1. If we plug these into the original equation, we can verify that they both check. We should probably consider an example in which one or more of the algebraic answers are actually extraneous solutions and have to be discarded. So let's solve the equation log of the fraction x plus 4 over x equal log x plus 1. First note that log without a specific base always means log base 10, which is called the common log. You will learn more about the common logarithm and its application in future courses and videos. However, all logarithmic functions are one-to-one, so we know that equal log values must have equal inputs. So we get that the fraction x plus 4 over x equals x plus 1. This is a rational equation which we already know how to solve. We can multiply both sides by x to eliminate the fraction, and then distribute the x on the right-hand side to simplify the expression. We then have another quadratic equation. Subtracting x and 4 from both sides gives us a quadratic equation in standard form that fortunately factors. Replacing x squared minus 4 with x minus 2x plus 2 gives us a product equaling 0. We set the factors equal to 0 and solve for the variable. we get that x equals 2 or x equals minus 2, but we must check these in the original equation. A check will verify x equal 2 is a solution, but x equals negative 2 makes the inputs into the logarithmic function negative. Log of negative 2 plus 1 doesn't exist, therefore the only solution is x equal 2.